Welcome back to Codex. Our talks this summer feature graduate students and postdocs who were nominated to speak by their senior colleagues. Today we have Hricha Acharya, who currently is a graduate student at Arizona State. She will tell us about median eigenvalues of graphs. Take it away, Hricha.
Thank you, Dustin, for introducing me, and thank you all the organizers for having me in the seminar. As Dustin mentioned, today I'll be talking about median eigenvalues of the graphs, and this work is joint work with Benjamin, who was an undergrad at ASU, my advisor Zilin, who is somewhere in the audience, and another graduate student, Shengtong, from Stanford University. So I'm sure a lot of you must be familiar with what adjacency matrix and eigenvalues of graphs are, but this is just a short introduction to get everybody on the same page. So an adjacency matrix for a given graph, we define it as an n cross n matrix, where every time you have an edge between the vertices I and j, the ijth entry is 1, and we put an entry 0 otherwise. So let's look at a small example. Here I have a triangle C3, and its adjacency matrix is a 3 cross 3 matrix. Observe that all the diagonal entries are always going to be 0, because whenever I'm considering simple graphs, that will be the case throughout this talk. And because it's a complete graph, everywhere else you're going to have 1. Since these matrices are always going to be real and symmetric, our spectrum is also going to be real, and that's why I can arrange them in all the eigenvalues in a decreasing order from lambda 1 to lambda n, like so. So eigenvalues can tell us a lot more than you would expect. So here I have a few examples. I have an edge, a square, a diamond graph, and also a Peterson graph, along with their eigenvalues, the spectrum respectively. So here are two classical results to sort of motivate spectral graph theory. So one of the first results is that the largest eigenvalue of my graph always lies between the average degree and the maximum degree of the graph. Usually lambda L is equal to the average degree and maximum degree whenever you have a regular graph. So for example, in the case of edge, you have largest degree 1. In the case of my square graph, you have largest degree 2, which is also the average degree. Similarly, for the Peterson graph, you have the largest degree and average degree 3. But for the diamond graph, my average degree is 2.5, the maximum degree is 3, and my lambda 1 sits comfortably between that. Another classical result in spectral graph theory, which kind of motivates the connection between the structure and the spectrum of the graph, is the result between bipartite graph, which basically says that whenever G is bipartite, then you're going to have your spectrum symmetric about 0, and vice versa is also true. So an example here would be your edge as well as the square graph, where clearly you can observe my spectrum is symmetric, but which is not the case with the other two non-bipartite examples that I have here. Uh, I would like you to I'd like to pay attention a bit more to the edge, whose spectrum is going to be 1 and -1. This will be relevant for us later in the talk. So why do I care about median eigenvalues, or what are median eigenvalues in the first place? So if I arrange my eigenvalues of my graph from the smallest to largest on a number line, the eigenvalues sitting in the middle are what I'm going to call the median eigenvalues. So whenever you have odd number of vertices, this is going to be 1, exactly 1, a median eigenvalue. And in even graphs, you're going to have 2 of them. So here's just other examples. So again, I have the square graph whose median eigenvalues are both 0. In case of Peterson graph, you have, again, 10 vertices. So you have 2 median eigenvalues. Both of them are 1. And in case of a complete graph, you have the 1 median eigenvalue because you have 5 vertices, and that is going to be -1. So as someone pointed out before the talk, usually people study the extremal, extreme eigenvalues, that is either the first two eigenvalue or the smallest eigenvalue. But today we are going to focus on the middle of the spectrum, that is our middle two or one eigenvalue. And to sort of motivate why we want to study this, I think the best way is to look at where this interest in these eigenvalues started from. And surprisingly, it came from chemistry, so the connection between graphs and molecules, which you might have seen in your high school in chemistry. So the origin of this problem comes from somebody relating Huckel molecular orbital theory to the subcubic graphs, those that is graphs with largest degree 3, where every organic molecules, those are carbon molecules, their skeleton can be thought of as these subcubic graphs. Here I have an example. This is a C60 molecule called Buckminster fullerene molecule. And each of these vertices are basically carbon atoms. And the edges here, which are molecular bond. So the skeleton of this molecule can be pictured as a subcubic graph or cubic graph, more specifically for this example. So what happens is the pi electron energy level, this is what chemistry people care about, have a one-to-one correspondence to the eigenvalues of these graphs. By eigenvalues, again, I mean the adjacency eigenvalues. More particularly, the highest molecular occupied molecular orbital energy is lambda h, the larger one of a median value, and the sorry, this should be lowest unoccupied molecular orbital energy would be lambda L, which was the lower one of our median eigenvalues. And actually, the molecular reactivity is what is governed by the difference between these two median eigenvalues. So that is why people started caring about how this gap behaves. More particularly, can we even bound these eigenvalues lambda h and L? This motivated mathematical chemists, Fowler and Pisanski, to run some computational experiments on some small graphs up to 20 vertices. And they observed that for almost all of these subcubic graphs, the median eigenvalue always lied between -1 to 1. And the only exception that they could find was this Heawood graph, which is a graph on 14 vertices and it's bipartite. And its median eigenvalues are square root of 2 and minus square root of 2. So this led them to formalize this as a conjecture and state that for all except finitely many subcubic graphs, your median eigenvalues are always going to lie between the interval -1 to 1. Eventually, over the years, a lot of partial results existed in proving this conjecture. Notably, Fowler and Pisanski themselves proved this conjecture for all subcubic trees. Mohar in 2013 extended this result to include all bipartite planar subcubic graphs with no exceptions. And in 2016, he showed that all bipartite subcubic graphs follow this conjecture, with the sole exception being the Heawood graph over here. Few of the other partial results also exist for non-bipartite cases, but the major non-bipartite case remained open for this conjecture. And that is exactly what we settle completely. So what our result states is that for all connected subcubic graph, except the Heawood graph, the median eigenvalues always lie in the range -1 to 1. So basically, because Heawood graph is a bipartite graph, we can say that for all non-bipartite graph, your lambda, L, and H will always lie in the range -1 to 1. Let me bring your attention a bit longer on this exception, that is my Heawood graph. If I want to include this exception in my result, I would restate it something like this. I would say that whenever my largest degree is bounded above by D, which is equal to 3, the median eigenvalues would lie in this range from minus square root of D minus 1 to square root of D minus 1. Another thing I would like to point out that this Heawood graph actually sits in a family of graphs. which are called the incidence graph of projective planes, and Heawood graph is the incidence graph of a Fano plane, which is a projective plane of order 2. In general, why this family of graph is relevant to us is because all the median eigenvalues of incident graphs of projective planes of order d minus 1 are exactly plus minus square root of d minus 1. So every time you pick a d, you will find an incidence graph of projective plane and whose median eigenvalues are equal to square root of d minus 1. So So beyond subcubic graph, if you want to ask this question about how the median eigenvalues behave, we again have this conjecture by Mohar, which states that whenever you consider a d greater than or equal to 3, and you have a graph whose maximum degree is bounded above by this d, the median eigenvalues actually lie in this interval, which is again governed by my maximum degree d, the bound on my maximum degree d. In fact, Mohar, along with Teifer in 2015, was able to show that this bound is tighter in case of bipartite graphs, where you can bring the bound to square root of d minus 2 and from minus square root of d minus 2 to square root of d minus 2. And again, the only exception being the incidence graph of projective plane of order d minus 1. So the question remains, what about the non-bipartite graphs with bounded degree d? And in that case, we answer the question partially. That is, we can say that the conjecture holds for all but finitely many values of d. In particular, we prove this in two parts. So we show that upper bound holds for all values of d. That is, my lambda h is always less than square root of d minus 1. But the lower bound we can show for partial cases. That is, we can show that the lower bound holds for all d greater than or equal to 75, for all integers d, where d minus 1 is a perfect square. So this includes cases which are also smaller than 75, for example, d equal to 5, and for some special graphs d which are triangle free. So irrespective of what d is, if my graph is triangle free, I can show that lambda L is greater than or equal to minus square root of d minus 1. So the remaining part of the talk is broken down into two parts. In part one, I'll briefly discuss the ideas behind the proof of our subcubic graph case. And in the second part, I will go and discuss some of the proof ideas that we use to prove the general result. So before I move on, are there any questions? Okay, so if there are none, let us move on. So let's focus on the proof ideas to show how my median eigenvalues can be bounded for the subcubic graphs. Let us start with a subcubic graph G. Here I have a small example of one. I can then have a maximum cut of the subcubic graph, which gives me a partition of my vertices into set A and B. What I need to observe here is that the graph induced on each of the set A and B is just going to be a bunch of edges and independent vertices, always. If you recall, I mentioned that the eigenvalue of my edge is always 1 and minus 1, and for an independent vertex is going to be 0. So for the graph induced on the vertices of A and B, all of its eigenvalues are going to lie in the interval minus 1 to 1. Now, suppose if this maximum cut gives me an unbalanced partition, that is exactly one of the part is strictly greater than the other in size, then Cauchy interlacing theorem gives me some bounds on my median eigenvalue immediately. So here I have my spectrum of graph G, like so. And what Cauchy interlacing theorem tells me is that my lambda L is bounded below by the smallest eigenvalue of graph induced on A. Similarly, my lambda H bounded above by the largest eigenvalue, lambda1 of G of A. And because each of this eigenvalue is bounded above by 1 and -1, that gives me that my median eigenvalues are also bounded by 1 and -1 from above and below, respectively. Observe that every time you have an odd number of vertices in the graph, the maximum cut is always going to give you an unbalanced partition. So Cauchy interlacing theorem immediately gives us the required result, that your median eigenvalues are always bounded in this interval. The real challenge occurs when you get a balanced partition, and which will only be the case when you have even number of vertices. Then the Cauchy interlacing theorem by itself is not enough for us, because then your smallest eigenvalue, or G of A, is only giving a lower bound on lambda h, not lambda L. Similarly, the largest eigenvalue of G of A gives you an upper bound on lambda L and not lambda h. So this by itself is not enough for our result. So all the work that we are going to do for moving forward is to deal with this particular case where you have a graph G, subcubic graph G, with even number of vertices, and the maximum cut that that it's given to you always gives you a balanced partition. The way that we deal with this unbalanced with balanced partition, sorry, this should be balanced here, balanced partition, is that we move some k vertices, vertex at D, from partition B to partition A, so that the kth largest eigenvalue of this graph induced on this new set is less than equal to D, equal to 1. In terms of what is happening with the eigenvalues and Cauchy interlacing theorem, what it gives us is that now this kth largest eigenvalue gives an upper bound on lambda h. And because this is bounded above by 1, we immediately get that my lambda h is also bounded above by 1. So now the goal sort of becomes for us is to find a positive tail reducer, that is this vertex set D, which I'm going to call the positive tail reducer, which we want to move from the set B to A. And observe that because my graph is not bipartite, so the spectrum is not symmetric. So we need to play this similar sort of game on also finding a negative tail reducer. But the idea is similar, so the proof structure will also follow the same. So just to give you an idea of the proof, we are going to stick to finding the positive tail reducer D. Okay. So now let's just to take a step back and give you a picture. Our goal is that we have some maximum cut of subcubic graph, which is balanced. And our goal is to find a positive tail reducer D, which has the properties like so. One thing that we need to take care of, or the sort of rule of this game that we can establish, is that whenever we are moving vertices from one set to the other, we need to make sure that accidentally we are not creating a new cut set, which is larger than the original one that we started with, because that's kind of like the contradiction. So our maximum cut argument fails there. So the rule, whenever we're trying to find the goal or achieve the goal of our game, we also always make sure that we cut the cases where you have a cut enhancer C, that is a set C, basically moving one vertex to the other gives us a larger cut set. Okay. So let's look at a small example of how we go about finding this tail reducer while making sure that we follow this rule. I want to show that if I have an edge AB in my graph induced on A, then the vertex A has degree 3 in G, or the vertex A itself is a tail reducer. So let's start with the first case, that what if my degree is equal to 1? Then I have an edge, both of them lie in my set A. If I simply move A from the red set to the different set over here, this edge AB becomes a cut edge, and that increases the number of edges in my cut edge. So A itself is a cut enhancer, so it kind of breaks the rule. So case 1 cannot happen. In case 2, now we assume that the degree of A is equal to 2. That means that A has a neighbor C in B. So I'm denoting those by blue vertices. So in particular, if we observe this vertex set C, it can have an edge in the B itself. That is a blue vertex adjacent to C. In that case, if I just flip the colors of A and C, that is move A to the blue vertices and move C to the red vertices, all these 3 edges become part of my cut set. So it's enhancing, it's giving us a larger cut set, which is again a contradiction and breaks our rule over here. The last case is when C has no neighbor in B. That is, all the neighbors in C are somehow all lying in the red vertices. In that case, we get that moving A to the blue set gives us a tail reducer. That is, it follows the goal. It achieves the goal that A itself is the positive tail reducer. So every time we want to show certain lemma, this is the kind of game that we want to play, that we want to achieve the goal. And we start with this local edge, and we kind of grow our graph locally and either say that certain case cannot exist because you can find a cut enhancer, or you terminate our search by finding the right tail reducer. In order to keep track of all these cases and what is going on, we have a bookkeeping tool that we introduced called the multigraph M, which is nothing but the edges of my graph GA union GB just become the vertices of this new graph N. So alpha is a red edge, that is an edge in A. Beta is a blue edge, that's an edge in B. And now they become a red vertex and a blue vertex, respectively. And every time you have an edge between them, you just put an edge between these 2 vertices in the multigraph M. So, and one thing to notice that because you're considering G to be non-bipartite, M is always going to be a non-empty graph. So now I use the multigraph M to basically break down my case analysis into these small lemmas. And in each of this case, that is, if I want to show that M has no multiple edges, or in each of the case that M has an isolated edge, I play the same game. I make sure that I don't violate the rule, that I have no cut enhancer, and I show that every time I can find a tail reducer in each of these cases. And this way we cover all the cases when you have large cycles, large paths, or even small paths of length 2, 3, 4, and so on. So this case analysis is quite extensive, and it can go up to 8 levels deep for both finding positive tail reducer and negative tail reducer. And the paper has like about 50 pages of work that we have done behind this. So it can be quite a tedious work if you want to read as so to make this work a little easier on the reader, in the more recent archive version of our paper, we have included a lean formalization of this proof. What it basically does is that you give it does all the work for you. So it's basically playing the game for you. It's finding the right tail reducer for you while keeping in mind that you're not breaking the rule of finding breaking the rule that there exists no cut cut enhancers. So that is the main idea that we work on this proof for finding the bounding the sub median eigenvalues of subcubic graphs. And I would like to point out that all these arguments are done locally. So you are only locally making sure that you are not getting any cut enhancers and just locally increasing your search and trying to find the trail reducer. So before I move on to the second part of the talk, Are there any more questions? Okay, so if there are none, so let's move on to the second part of the talk, where I want to talk more about the generalized results, where you no longer care whether your largest eigenvalue is bounded above by 3, but you want to make more general statements about what if I'm bounding my largest degree by some d, which is real. So let's start with the conjecture. And so beyond subcubic graph, let me first explain why the same ideas that we used earlier may not be the first choice or not the best choice to move forward as it is. Because if you observe, because as I mentioned, all of these arguments are local. So every time you want to deal with a new D, it's quite an extensive work that you want to put into it. On the other hand, let's suppose if we consider the case D equal to 4, and we consider the maximum cut of this graph, let's say AB. In each of the cases, we can also show that the graph induced on maximum degree 2. But Cauchy interlacing theorem is limiting in a way that it's only showing you the eigenvalues lie in the range -2 and 2, where we actually need it to lie between minus square root of 2 to 2. So it does not give us quite tight bounds that we want. So there is a need for some different techniques. And our approach uses some algebraic as well as probabilistic tools to achieve this goal. So let me give you an idea based on the proof of the upper bound for the median eigenvalues. So the upper bound basically says that every time you get a graph G whose maximum degree is bounded above by D. So for all integers D greater than equal to 3, your lambda h is bounded above by square root of D minus 1. The goal here is a probabilistic argument where we want to show that all the eigenvalues which are strictly greater than this upper bound, they can only be less than n by 2 of them. Less than half of the eigenvalues can be strictly larger than this upper bound. So our goal is to show that the probability that eigenvalues lie in this interval is strictly less than half. So to start this proof, we start with a magic polynomial f of x, where the roots are minus d, two of them are minus square root of d minus 1, and we quite cleverly pick alpha to be f of such that f of square root of d minus 1 is equal to f of d. To give you a visualization of what this polynomial actually looks like, between the interval of interest minus d to d, which is where all my eigenvalues are going to lie. So the two key observations here are f of x is always positive on this interval, and between square root of d to d, my f of x is always going to be larger than the value at f of d. So these two sort of observations or consequence of choosing our polynomial f of x to be so, we'll see are useful later on in the proof. So I talked about giving you a probabilistic method. So here's the probabilistic perspective to this problem. So we start by considering lambda to be an eigenvalue, which we are choosing uniformly at random from the set of all eigenvalues of my graph G. I can then evaluate its expectation of f of lambda, and which because is written like so. Because it's a quartic polynomial, we can write it as sum of lambda I to the power 4, lambda I to the power 3, and so on. And later, we can give an upper bound to this expectation in terms of d. This is because each of this term basically counts the number of closed walks of length 4, closed walk of length 3, closed walk of length 2 in my graph. So using the bounds on number of closed walk, we can give a bound on the expectation of f of lambda. Then we introduce a comparison random variable called mu, which takes value between these four integers, real numbers, and it has probability distribution like so. So this is not a random variable that we pull from air. It's actually very deliberately chosen and given this probability distribution, and it mimics the eigenvalue distribution of our extremal graphs. That is the incidence graph of projective plane of order d minus 1, whose median eigenvalues are exactly square root of d minus 1 and minus square root of d minus 1. We later get that the expectation of f of mu is actually equal to the upper bound of EF lambda. And the key result that we need to keep in mind for now is that this gives us an upper bound of our expectation in terms of f of d. So all this work we do to get that the expectation of f of lambda is less than equal to half of f of d. We then later bring this all together to force our bounds and show that the probability of my eigenvalue lying in this range times f of d has to be less than equal to half of ft, and we get the conclusion that we wanted to enforce from the beginning. We have achieved our goal. The same proof can be used to prove the case where you consider G to be a triangle-free graph by flipping all the eigenvalues from lambda to minus lambda. But we cannot extend this result to a more general setting, that is graphs which might contain some triangles. So there you want to use a little bit of different methods, while still keeping the gist of it together. But before I move on, are there any questions over here? Okay. So moving forward, now let us talk about the lower bound on my median eigenvalues. So here I want to show that whenever my integer d is greater than equal to 75, my lambda L is is greater than equal to minus square root of d minus 1. So the proof here is a little different because we start with the assumption for contradiction that lambda L is strictly less than minus square root of d minus 1. And the way we move forward is we develop this integrality anchor. We basically say that because all my eigenvalues are real, because we started with a real symmetric matrix, that was the adjacency matrix, the characteristic polynomial has integer coefficients. And specifically, if we only choose the eigenvalues which are not equal to square root of d minus 1, then I can say that this product is greater than equal to 1. Moving forward, I'm going to split this product into two parts. So one of the factors I only care about the plus terms, and here I'm going to care about the minus term. And we get that this is greater than equal to minus 1, greater than equal to 1. So the whole argument basically rests on breaking this integrality that we get over here. In short, what I want to show is that I can force these two factors to be small enough such that the product of these two factors turns out to be strictly less than 1, and which breaks our initial assumption, giving us our result. So the way we kind of break this integrality argument is as follows. We lean heavily on bounding the graph energy. So what is a graph energy? Graph energy is nothing but sum of all absolute values of eigenvalues. But the average energy is just dividing it by the number of vertices. We give, similar to the argument for upper bound, we can again develop this new polynomial and give a sharp bound over average energy for a graph. This upper bound is tight because for the extremal graphs, the average energy is exactly equal to this upper bound over here. We then use this upper bound for average energy and the AM-GM inequality to basically show that these factors, each of these factors are quite small, and in turn, we show that the product has to be less than less than one, forcing us to know that our initial assumption that the initial assumption, sorry, initial assumption that lambda L is strictly less than minus square root of d minus 1 is untrue, and hence we get this upper bound. One more thing that I would like to point out here is there's nothing really special about this d equal to 75. It's just the argument that we do here spits out that number. But I believe that, or in general, we believe that this lower bound should be true for all d, which is also what we see in some of the sub results for other lower bounds that we have seen before. So just to summarize, we started with the spectrum of the graph on n vertices. We can arrange them from lambda 1 to lambda n in the decreasing order like so. We define the median eigenvalues to be the ones sitting in the middle of this arrangement of our eigenvalues from lambda 1 to lambda n. Then we show that for all subcubic graphs, that is graphs whose degree is bounded above by 3, the median eigenvalue lie in the range -1 to 1. The only exception to this rule is the Heawood graph. Heawood graph is actually part of a pattern, and it sits in the family called as the incidence graph of projective planes of order d minus 1. And in general, for all d greater than equal to 3, if a graph has delta less than equal to d, we have the conjecture that eigenvalues, median eigenvalues lie in this interval. We can show the conjecture for to force lambda h to lie in this interval. And we can show that for d greater than equal to 75, when d minus 1 is a perfect square, and when G is a triangle-free graph, lambda L is greater than equal to minus square root of d minus 1. And I would also like to point out one final time that the only known extremal graph to this conjecture in each case of D is the incidence graph of projective plane of order d minus 1. So moving to the open frontier or the open questions in this field. The first and the most obvious being, can we show that this interval or the conjecture holds true for all Ds? Specifically, the 64 finite values of D remain open here. That is those which are D less than 75 and those which are D minus 1 is not a perfect square for them. So I believe it should be possible to prove, but we might need maybe a more structural argument for that because the current methods that we have is probably not the right tool that we are hitting the problem with. But I have like quite a strong confidence that it should be true and we should be able to prove it. We having someone. And are there infinitely many? The next question would be, are there infinitely many graphs whose largest degree is bounded above by D and the median eigenvalues are exactly plus minus square root of d minus 1? Because the only known graph to us are the incidence graph of projective plane, it would be interesting to know if there exists like a family of infinite graphs or maybe infinitely many graphs who have exactly these median eigenvalues over here. The next question is, if the answer to the two is false, that is, there are only finitely many such graphs, then can this bound be improved further? For example, in the case of bipartite, this was true, as in the bound was improved further with the only exception, with only one exception. So can we, if the answer for question 2 is false, then can we improve the bounds on median eigenvalues further, maybe for some specific family of graphs, as was in the case of bipartite graphs? So these are some of the open problems that are like a beginning of all the questions that you could move forward and talk about. And here are some of the references that I look at or I refer to throughout the talk. And thank you so much for paying attention. I will take any questions that you have now.
All right, let's thank the speaker.